So I mentioned on a previous example that the probability that an event does not occur is 1 minus the probability it does, because either it occurs or it doesn't. We add that up. One of those two things has to happen 100% of the time, right? So the probability that an event does not occur can be computed as 1 minus the probability that it does. Okay? And sometimes that's the easiest way to compute it. Just to see that that makes sense, I have an example where we could count it both ways and see that it works, right? Suppose we roll a single die. The single of dice is die. So you have 6 possibilities of what could happen. So the probability I get any particular number, but let's say a 4 here, the probability I get a 4 is 1 out of 6, okay? Or 16.6 repeating percent, 0.16 repeating. The probability I do not get a 4, we could do 1 minus 1/6 or 5/6. But we can also see there's 5 ways to not get a 4, the other 5 numbers, out of the 6 possible numbers. So the probability something does not occur, sometimes it might be easier just to look at the sample space, but you can always do 1 minus the probability it does occur. Okay. Here's an example. Now this is an empirical example. A lot of times in medicine we have to do empirical probabilities, but here's an example of using that. So suppose that a 50-year-old man has systolic blood pressure of 110 and that 60% of his cholesterol is HDL. The risk of heart attack in the next 10 years is given in the table. Now what they would do is take a large number of men meeting these criteria, track them, and see how many had a heart attack and get what are called empirical probabilities on that. That's how you would get a probability in medicine. You would just look at a very large sample and see what happens. But if a man satisfying these conditions is selected at random and has a cholesterol level of 250, what is the probability he will not have a heart attack by age 60? So he meets the criteria to where we could look in the table and we see the probability that he does have a heart attack is 3%. We can just read that in the table. If we want the probability he does not, we just subtract from 1 or from 100%. So the probability of no heart attack is 1 minus the probability that does have a heart attack. So 97%, or as decimals, 1 minus 0.03, 0.97. So there's a case where I can use the 1 minus rule to figure out the probability that it does not happen. Next, I mentioned we're going to get some rules for and or, and we'll get the more general rules coming up, but right now we're going to look at a specific case. We have a definition here of events being mutually exclusive. Okay? So the term mutually exclusive for 2 events means they cannot occur at the same time. And I often use mutually exclusive and disjoint as synonyms to mean the same thing. Technically, mutually exclusive refers to events, disjoint refers to sets, but sets are how we count the probabilities anyway. So basically mutually exclusive and disjoint both mean they don't overlap, they can't occur at the same time. So by definition, if they're mutually exclusive, the probability of E and F would be 0. They cannot occur at the same time, so the probability would be 0. Just the way that it works out of counting it up, you don't get any overlap. So the probability of E or F would be the sum of the 2 probabilities. If you looked at it in terms of the formulas, you'd have common denominators and you just add them together. As long as they're mutually exclusive, there's no overlap. We'll see in general, we just have to subtract off the overlap when we look at the more general formula. But if they're mutually exclusive, you can just add the probabilities together. And that's defined in terms of 2 sets, but you can be more general. A set of N events are mutually exclusive if none of them can occur at the same time. And the probability of, say, E1 or E2 or all the way up through En would be the sum of the probabilities. And there we have the symbols. The one that kind of looks like a U is the set symbol for a union, which means or, E or F. I could write E, the union symbol, F, or use the word or. The upside down one is the intersection symbol, which goes with and that we'll see at some point in the notes. But if events are mutually exclusive, you just add up the probabilities. Okay? So find the probability of rolling a 1 or a 3 on one die. Okay? Those are mutually exclusive. I can only roll one number at a time. There's no way I can roll a 1 and a 3. So I would just add the 2 probabilities together. Okay? If I want to use the formula, the probability of rolling a 1 or a 3 would be the probability of rolling a 1 plus the probability of rolling a 3, which would be 1/6 plus 1/6, or 2/6, which is 1/3. There we can also verify from the sample space. If you want to roll a 1 or a 3, well, there's 2 successes out of the 6 possibilities that would make that happen. Okay? Find the probability of rolling 2 distinct dice and obtaining a sum less than 6. Okay, so that's the more complicated sample space we looked at earlier. Let's look at the picture. We want a sum less than 6. Okay? So if we look at this, the possible outcomes are 2, 3, 4, all the way up to 12 if we have a 6 and a 6. So a sum being less than 6, it can't be a 1. The sum would be at least a 2. So it could be a 2, 3, 4, or 5 and be less than 6. Since I'm going to get a unique sum, they're mutually exclusive, so my probability would be the probability of rolling a sum. We're looking at the sum here, okay, of 2 plus the probability of getting a sum of 3 plus the probability of getting a sum of 4 plus the probability of getting a sum of 5. Okay? And we could count all those up, and there's a very nice pattern to it if you look at it. There's only one way to get a 2, to get the snake eyes there. There's 2 ways to get a 3. If you go along the diagonals, there's 3 ways to get a 4, 4 ways to get a 5. It goes all the way up till you get down to 7. There's 6 ways, and then it starts going back down. But it winds up being 1 out of 36 plus 2 out of 36 plus 3 out of 36 plus 4 out of 36. We've got a common denominator. It adds up to 10 out of 36 or 5 out of 18. Here I slashed through the ones that would be a success. Okay? So there winds up being 10 of those out of the 36. And then just to summarize a little bit here, so probability rules, some things we've talked about. Your probability is telling you the chance that something occurs, and that's always between 0 and 1. Okay? You can't have a negative probability, and you can't have more than 100% chance if you write them as percents. So they got to be between 0 and 1 as decimal numbers. And then the extremes pointed out here, the probability of the sample space, just meaning the probability that something occurs, is 100%. Okay? So 1. So if an event has to occur, its probability is 1. Don't have it written again here, but 0 means it's impossible. Okay? And then if A and B are disjoint or mutually exclusive, the probability of A or B is the sum of the 2 probabilities. And then the probability that A does not occur is 1 minus the probability that A does occur. Because kind of combining the ideas there, A and not A are disjoint. They have to add up to 100%. Then I just have a couple of extra slides with some terminology I'll throw up here. Everything in this section, and the next section for that matter, we're going to be looking at what are called discrete probabilities. And you can read through the slide there, but discrete, we can count them. We could actually list the things that are in the sample space and count them. Okay? It's not a continuous variable that can take on the infinitely many values and the whole number line. Okay? So the ones that we can count and find the probabilities, they're called discrete. Otherwise, you have what's called a continuous random variable, which is much more complicated, and we will eventually look at those, which are with what are called density curves. We're going to look at the normal distribution, which is the most popular density curve that you're going to see. We'll look at that when we go back and do Chapter 3. There's a reason I'm saving Chapter 3 in this class until later. It's a little more complicated idea than looking at the discrete sets. But if you want to define continuous probabilities, you can't count everything because there's infinitely many, so we have to use what are called density curves and find areas under the curves ultimately uses calculus, but we can use tables and calculators and statistics to do it. Okay? So that wraps up our first introduction here on probability.